Today we are going to talk about the Z transform. Okay, and what is the Z transform? Just like the Laplace transform, that is extension of continuous time Fourier transform, and Z transform also, that is the extension of discrete time Fourier transform. Okay, we will see more details from that transform. And remember that for the LTI system, if I send Z to the n, or this eigenfunction e to the j omega n, to the LTI system, this is LTI system. And then what is your output? Because this is LTI system, and those are the eigenfunction. So the output is still Z to the n and e to the j omega n, but I have the eigenvalue, something the coefficient times Z to the n. Times this complex exponentials. And what is Z? The Z is a complex number. And for this h, how do we find this function? For h, this is the Z here is just the Z transform, n from minus infinity to infinity, h n Z to the minus n. Okay, this is the Z transform. What is e to the j omega n? Oh, what is e to the j omega? E to the j omega, if you take the magnitude at 1, right? So it is a unit circle. So now let's just talk about the Z transform. Okay, what is the definition of the Z transform? X is a discrete time signal. Okay, and we define that the Z transform is your signal times e to the minus z. This one, xn, n could be x0, x1, x2, or x minus 1, right? Those are the values. So values times z to the minus n. So this is the values. Then you can see that if it is the value, and what is this summation? This summation is what? Something z to the minus 3 plus something z to the minus 2 plus something z to the minus 1 plus something something times z to 0 plus z1 something, and the coefficient z2, and so on. This is like a polynomial of z. Well, z polynomial. So for the Z transform, maybe it is easier for you to imagine rather than Fourier transform or Laplace transform, because this is just like a polynomial, which means I put here. Okay, this is the n. So I may have 0, maybe 1, 2, 3, minus 1, minus 2, minus 3. So here is n equals 0, 1, 2, 3, minus 1, minus 2, minus 3, and so on. And what is, when n equals 0, that is z to the minus 0. Okay, so here is z to the 0, and this is z to the minus 1, z to the minus 2, z to the minus 3. This one, minus 1, this is z to the 1, z squared, z cubed. So you can see that overall this is the z polynomial. In the discrete time Fourier transform, when z is e to the j omega, well actually z is e to the j omega, so we have e to the minus j omega n. Okay. And in this case, the magnitude of z is 1. Okay, so because this is the unit circle. Okay, so when we talk about the Fourier transform in the past, actually we talk about that unit circle. But now for the z transform, our z, we have r. We have the radius. Okay, in this case, the z becomes r to the r times the unit circle. So if we rearrange that here, that is the basis. So this is the extension of the Fourier transform, right? We have the Fourier transform of this one. So here is the discrete time Fourier transform. Discrete time Fourier transform of x r to the minus n. So that means in the past, we have this unit circle, and here is 1 0, a 1 0. This is the unit circle. C equals e to the j omega. But now, what we will extend it to all the plane. So we have R, because this one, R is 1 for the discrete time Fourier transform. But now we extend to the whole plane. Z is R e to the j omega. Okay, this is omega, and the length is R. Let's see here. In the past, for the discrete time Fourier transform, okay, we focus on this unit circle, Actually, if we cut it here, we cut it. So from 0 to 2 pi, periodic. But now we extend it to, like for example, R1 here. It could be also like smaller one, but we just plot it R1. Easier to see the shape. Still from 0 to 2 pi, but this is the Fourier transform of xn times R1 to the minus n. Okay. Therefore, we write it down here. We know x R1 e to the j omega. The z transform is R1 e to the j omega minus n. This is this a basis? No, this is not the basis. Okay. Because if we take the conjugate R1 e to the j omega to the n, let's take the conjugate. That is R1 n e to the minus j omega n. But here is we still have r to the minus r1 to the minus n. Okay. So it is not the basis. However, if we think xn and r1 minus n together times e to the minus j omega n. This is the basis. Okay, which means this is the basis. If I want to get this coefficient, your function in the product, your basis. But here I cannot find this xn, the coefficient, using this, because this is not the basis. Okay. So in this case, we can also get the coefficient, but what coefficient? Overall, this coefficient R1 minus n will be 1 over 2 pi, your function in the product, the conjugate of your basis. This is still a basis. So those are not orthogonal, okay, because they are not the basis. Not orthogonal. If we see this in 2 dimension, you will see, well, we don't have space, maybe here. This is the real part, and here is the imaginary part. The green one with R1 here, and then the unit circle, For the Z transform, it may not be well defined, or it may not be converged for all Z. We will see some examples later. But this Z transform may converge at some region of Z plane. Well, like sometimes maybe Xn, this signal doesn't have the Fourier transform, but they have the Z transform. So we can see more information for that. This is parallel to the Laplace transform, so you can almost like apply everything to a Z transform, but instead of consider the S plane, now we care about this J omega to be a unit circle. Okay, this one will go to this unit circle, and we will see the regions of convergence. Let's just see two examples first. How do we find the Z transform? So first, let's find the Z transform. A sequence times the unit step function. So here, by the definition, the Z transform only when n is greater than 0, I have a value. Okay, so just one more step. N from minus infinity to infinity. Here we have 1 over 2 to the n u n z to the minus n. So we only have values when n is greater than or equal to 0. So here you have 1 over 2z to the n. You will get 1 minus 1 over 2z to infinity, and 1 minus 1 over 2z. When is it valid? Okay, now think about this. So actually this is 1 over 1 minus 1 over 2z. You will get 2z over 2z minus 1. So here's a condition when this holds. If the ratio, okay, this ratio is less than 1, right? So when the ratio is less than 1, which means the z is greater than 1/2. This is your region of convergence. So if we plot, let's plot here. If I have, this is 1/2. Then region of convergence, that's outside. So here. Next example. Okay, find the Z transform. Still, let's use the formula and see what happens. So again, this time I have the unit step function, but I have minus n. So that means, and also shift. So only when n is negative, I have a value. Otherwise, it is 0. So here, we plug in minus u minus n minus 1, 2 to the n, 3 to the minus n. So I only have negative values till minus 1. The unit step function is 1. And this is 1 over 2z to the n. This gives you 2z minus 1. So you can see that I have the same Z transform, but actually you can you should know that the region of convergence should be different, right? When will this hold? When the ratio 1 over 2z is greater than 1. So which means this region of convergence is inside the 1/2 circle. So it's inside. One half. So again, now for these two examples, you can realize that when you find the Z transform, you also need to give the region of convergence. With the same Z transform, we may have a different region of convergence. Okay, so you should include the region of convergence. For next example, let me see. Just tell me that what is the region of convergence? What is the region of convergence for this part? So here we should get, we can put 7 outside. 1 minus 1 over 3z. And the second one, minus 6, 1 over 1 minus 1 over 2z. Okay, so for this summation, to get this one, what is the region of convergence? The ratio should be less than 1, right? So 1 over 1 over 3z should be less than 1, which means z is greater than 1/3. And how about this part? 1 over 2z should be less than 1. So z is greater than 1/2. Therefore, the z transform is 21z over 3z minus 1 minus 12z 2z minus 1. Okay, then what is the region of convergence? Greater than 1/2? Right, because we need the intersection. Yeah, so we should choose this one, right? This one also includes this. So here, z is greater than 1/2. So here you can see that the region of convergence do not depend on the omega. Okay, you can think that if z is e to the j omega something, then it doesn't depend on omega. We will also see that in 2 minutes. Okay. Right, now let's see actually the relationship between the Laplace transform and z transform. For the Laplace transform, okay, we may see that we have right half plane, left half plane, and for the z plane, the left half plane is that inside the unit circle, and the right half plane is outside the unit circle. Actually, when the region of convergence that's less than 0, we have left half plane. They will map to z less than 1. So it is inside the unit circle. And it is greater than 0. That's the right half plane, which will map to z greater than 1. Alright, so now let's really talk about the regions of convergence for the z transform. Okay, the region of convergence of a z transform consists of a ring in the complex z plane. This is a z plane. Here's a ring. Okay, z transform is that the Fourier transform of xn times r to the minus n. So if I want this to be converged, this is bounded, we only depend on r, okay, not the omega. Okay, we need to times e to the j omega, and not the omega. We only depend on the radius. And then the inner boundary may extend it to 0, and the outer boundary may extend to infinity. So I may include the 0 as our region of convergence, and I may include the infinity as our region of convergence. Okay, so actually we have 5 different types, or 5 possibilities for the region of convergence. First, inside the circle, the unit circle, or outside the unit circle, or even like a donut. And for this too, it means the entire plane, including the infinity. And the last one is the entire finite plane. So that means I don't include the infinity. Okay. Does not include the infinity. And the region of convergence does not contain any poles. Okay, poles, that means in the denominator, which makes the denominator 0. Okay, then 1 over 0, that's not bounded. Okay, so the region of convergence does not contain any poles. If the region of the Z transform, normally you have a fraction, okay, because it is also easier to make it as a fraction because you can use the table to find the Z transform. The poles, what is the poles? The poles are the zeros of Q. It is in the denominator. So if the order of P in the numerator is greater than the order of Z of Q in the denominator, then we will consider that there is a pole at infinity. If X is finite, then the region of convergence is entire Z plane except 0 or a Z infinity. Or we may include that. For example, if I have a delta function like this, what is the Z transform? We have Z transform here, n from minus infinity to infinity, x and Z to the minus n. Okay, so we have delta function times Z to the minus n. So what is the answer for this? One. Okay, so in this case, the Z transform is 1. Then how about the region of convergence? So the region of convergence is entire Z plane. So it includes 0 and infinity. If I shift by 1, then what is the Z transform and also the region of convergence? Again, let's find the Z transform. Here we have delta m minus 1 Z to the minus n. Then here we have Z to the minus 1, right? This is 1 over Z. Then what is the region of convergence? Still entire Z plane, right? But when Z equals 0, that's in the pole, in the denominator, they will blow up. So our Z is entire plane but except Z equals 0. So not including Z equals 0. If I shift to the left, then we get Z. So the region of convergence is finite Z plane, which means infinity is not included. Questions about this? If not, we can take a break. Now, let's continue for the region of convergence. If the signal is right-sided, what is right-sided? Well, when the signal is 0, when n is less than some point, then what is the region of convergence? The region of convergence is outside the circle. This is R0. Okay, so it should be outside. If the signal is left-sided, then it should be inside. And if the signal is two-sided, then it's like a donut, or we said it's a ring. So for the right-sided, that means the region of convergence exists outside of some circle. And for the left-sided, that means the region of convergence is inside some circle. And if X is rational, P over Q then the region of convergence is bounded by poles and extended to either 0 or infinity. Read by poles because the region of convergence cannot include poles. We'll see the example right away. If Z is rational and also right-sided, then the region of convergence is the region outside the outmost pole. So it may include infinity. And then if x is 0 when n is 0, the region of convergence may also include infinity. Similarly, if the signal is left-sided, then and also rational, then the region of convergence is the region inside the innermost pole. You may include 0. For example, rational, that means I have poles and zeros. So suppose I have 2 poles, 1, 0, and then this is unit circle. Suppose this is a unit circle. Okay, so first, if x is right-sided, so here x is right-sided, where is the region of convergence? Here it says that outside the outmost pole, the outermost pole is this one. Right, so for the right-sided, outside the outermost, so outside the outermost, it should be here. If x is left-sided, left-sided, there'll be the innermost pole. Okay, inside the innermost pole. So inside should be here. So in this case, it's inside here. If x is two-sided, there'll be a ring, but they cannot touch the pole, so should be okay. So 3 cases. If x is rational, right-sided, outside, left-sided, inside, two-sided, like a ring. Right, now let's see the properties of the Z transform. So the Z transform X, we have region of convergence R. Another signal, I have a Z transform with the region of convergence R1, followed by another signal with Z transform X2, region of convergence R2. Linearity, okay, linearity, that's same thing as the Laplace transform. Okay, we do the linear combination, then in time domain, then in Z domain, it is also the linear combination. The region of convergence should be the intersection. We did this. Actually, we did this here. Okay, the intersection of two regions of convergence, but it could be greater than that when if we have pole zero cancellation, then the region of convergence may greater than the intersection of these two regions of convergence. And then time shifting. So if I shift in time domain by n naught, what happens? Magnitude is the same. I just have a phase shift. So the region of convergence still R, but we may have additional deletion of the origin or infinity. Okay, so for the time shift, you can think about, because the Z transform is like a Z polynomial. Okay, it's easier that you can draw it. So if I draw that, suppose this is n, okay, and then I have maybe this one, this one, okay, so if my index is 3, 2, 1, 0, minus 1, minus 2, minus 3. The Z transform here, minus 3, that's Z cube. Minus 2 is Z square. Minus 1, that's Z. And then 1, Z, minus 1, Z, minus 2, Z to the minus 3. Okay? All right, the value times Z cube, the value times Z square. Okay, what is X? If I shift by 1 to the right, so everything will shift to the right, right? So I should, you think that this I shift to the right, okay? So if I shift one unit, this is what? This is index 4. This is index 4, 3, 2, 1, 0, minus 1, minus 2, right? How about, I can also think of this as shifting the index. Because I shift to the right, I can also think of shift the index. So here will be 4, 3, 2, 1, 0, minus 1, minus 2. Can I change the color? Okay, so my Z transform will be Z minus 1 times X of Z. So this is Z square, Z and 1, and Z minus 1, Z minus 2, Z minus 3, Z minus 4. This is n minus 1. So I can also think of shifting the index. Okay. Right. So here, still times now this one. This one. So when n naught is greater than 0, okay, I shift to the right. So if I shift to the right, the poles at 0 may cancel zeros at Z equals 0. If n is less than 0, and not if I shift to the left, then I may have I may created the zeros at 0, and these zeros may cancel poles, because here that I may cancel something, right? If I times this and x is rational, so I may cancel something. So you can also think about time shifting is like shifting your axis. And I can also shift not right now. Now let's talk about the scaling. Compress or expansion. If I times z in time domain, which means that in z domain, it could be compressed, it could be expanded. Okay, and then the region of convergence is the original one times the magnitude of z naught. If you see the equation, if I do the z transform, you can rewrite this z transform as z over z naught to minus n. So if I have a pole or zeros at z equals a, then I will shift to z equals z naught times a for the regions of convergence. If this z naught is just a complex exponential, we only have the phase. Okay, I only have a phase shift, which means e to the j omega naught n times xn for the z transform. The region of convergence is still the same. But what do we do here? We just rotate in z plane. We rotate in z plane by omega naught. The magnitude is still the same. But if it is not in the imaginary axis, okay, now I have the radius. Then for your pole and 0, we'll also rotate. They are rotated by your omega naught, and also you scaled by the radius r naught. If I have, for example, like a poles or maybe zeros, if I scale by this, it is not just rotate. If we don't have R naught, this one just rotate. For example, they will rotate to here, maybe to here, and zeros. But if I have R naught as well, they were scaled. So they may from here to here, and then the zeros maybe to here. They may also scaled by R naught. Next one, the time reversal. For the time reversal, the region of convergence is also the reciprocal of the previous one. Think about this is x, and here I have value at -2, value at -1, value at 0, value at 1, value at 2, and value at 3. This is z 0, right? Z to the 0, z to the -1, z to the -2, z to the -3. Here's z, z squared 1, z cube. So if I have a time reversal, so here there'll be 1 over z. So they will just so they just switch like here and here because they do the reversal, right? And so that actually you can think about this, just flip. So they flip all these x's, which means if you are right-sided signal, then you become left-sided. Then you can also expect the region of convergence. In the past, it is outside, but now it becomes inside. So the left-sided, the region of convergence is inside. Okay. Time expansion. Okay, so here time expansion, this one is different than the Laplace transform. Okay, so here, if we define that x of k, this k is in the denominator. Okay, so it could be expanded or compressed. Then the z transform will be z to the k. And here is the region of convergence. Let's see an example. If I have this signal, original signal, then what does that mean? x2, k is 2. So there will be n divided by 2, which means the expansion. Okay, so the expansion, your signal becomes, so there'll be n over 2. So they will expand by 2, double it. So this one will go to here. And this signal will go to index 2. Wow, so in that case I can just copy. So they'll go here. and 0 is still at 0. So when x2, this means I insert k minus 1 zeros, which means 2 minus 1, 1 0 between the samples. If the real number, it is an integer. If this real number is one over m, then we will only keep every m samples. So that this is 2. So I insert 1 0 in between. But if it is like 1 over 2, we compressed. If we compressed, then we don't have these two values. We only have x2 and x minus 2. So and we also have 0. Next, for the conjugation, if my signal is conjugated in time domain, then in frequency domain, I also conjugate it, and also z, I need to conjugate that. Region of convergence should be the same. But if x is real, that means if I do the conjugate, it's still the same. So the z transform is still the same. If I have a pole or 0 at z naught, then we'll have a pole or 0 at z equals z naught conjugate. You can compare to this discrete time Fourier transform, Laplace transform, and z transform. If I conjugate, well, I do the same thing. Because if I conjugate in time domain, in z domain, let's see, this is by the definition, right? But I can manipulate this. We can think about this as the summation xn z conjugate to minus n overall conjugate. So xn conjugate and z conjugate and conjugate that cancel out. But what is this one? This is something conjugate, right? And this is the z transform, z conjugate transform. So this is x conjugate z conjugate. For the convolution, always that if you convolve in one domain, in the other domain they do the multiplication. Okay, and the region of convergence should be the intersection of the original two region of convergence, but it may be greater than that, because when we have the zero pole zero cancellation, so the region of convergence may be larger if pole zero cancellation occurs. Cancellation. All right, those are the properties, some important properties in Z transform. Now we just learned the Z transform, and we need to apply the Z transform to our system, the LTI system. Okay, like the Laplace transform, we need to check the causality and also the stability of the system. So again, that if I have a signal, I send it to the system. Then your output is the system convolved, the signal convolved the system function. How do I know the system's property, or how do I know the system's, I should say, how do I know the system's function? Yes, if I send the delta function, I can see the system, I can know the system, right? And then in Z domain, the output is the multiplication. Okay, here is the system function. Or the transfer function. First, for the system causality, a system is causal if and only if the region of convergence of the system function is the exterior of a circle, including infinity. So in this case, and also that may extend to include the origin, or in some cases. In this sentence, what does that mean? The region of convergence is the exterior of a circle, including infinity. Then is the system, the signal, right-sided or left-sided? H over n should be left-sided or right-sided? So here we said it is right-sided, okay. if the system is, this function is rational, then first, the region of convergence is outside the outermost pole. Okay, because region of convergence cannot include the poles. And also the order of numerator cannot be greater than the denominator. And we can also say that if the system is causal, that means it is right-sided, but the other way around is not true. Just like the Laplace transform, right-sided if it's starting from -3. And this is not causal. Okay? For stability, a system is stable if the region of convergence include the unit circle. Once they include the unit circle, it is stable. And then for the causal system, and the transfer function is rational. With this, we say this is stable if and only if all the poles lie inside the unit circle. If I have a pole outside the unit circle, then it is not stable. Because for stable, I need to include the unit circle, right? If I have a pole here, and also I need right-sided. If I have a pole here, then at least I need this one. And this is a unit circle, I cannot include that. So all the poles should be inside the unit circle, right? Because still remember, the region of convergence is outside the outermost pole. Alright, so now let's see the LTI system. For the discrete signals, we have difference equations. Here's the difference equations. If I take the Z transform, here's the result. Then we can find the transfer function. This is a transfer function. You can see that that's why that most of the time you will see a fraction. H is rational. So we need some constraints, additional constraints, to determine the region of convergence. And this is in the numerator, so we have zeros. In the denominator, here we have poles. Suppose the system is stable, we want to find the impulse response. Impulse response, that's H. Okay, what is the impulse response? If I take the Z transform, we have 1 minus 1/2 Z to the minus 1. And 1 plus 1/3 Z to the minus 1. So the transfer function we will get 1 minus 1/2 z minus 1. We can use the table to find it, and then in this case, you can check the table. Okay, we will provide the table in the exam, so you'll get the impulse response. Right, let's see this example. We can also review how do we do the convolution. I have an input, okay, with duration 2 seconds, and then I to the integrator, okay, XA, and the output of XA is sampled by every 1/2 seconds. So to form this, so the sampling rate is 2 samples per second. First, we need to stem plot of the discrete time signal. Okay, so make sure that you add this sentence. Right, so I have an input. I send it to a system to get x of a. So I send it to here. So what is this system? I can send the delta function to check this impulse response. So first, 2, here t minus 2 to t, delta function d delta, d tau. We get either 2 or 0. So when t is between 0 and 2, we got 2. Otherwise, it is 0. So what is XA? In time domain, we do the convolution. In frequency domain, we do the multiplication. But here we can do the convolution. X convolved H. Okay, we found the H. What is H? A square, a rectangular. Okay, so this is H. Okay, this is just here. And what is X in? UT minus UT minus 2, which is here's 1, here's 2. If I convolve this 2, what do we get? We have a same width, right? So it is not trapezoid, it will be a triangle. So we will get here is 4. And this is 2, and here's 4. Next, I sampled every 1/2 seconds. So I sample every 1/2 seconds. That means this is 2. Every 1/2 second, this is 1. 1/2, 3/2, 3, 1 1/2, 5/2, no, 3/2. So this is 1, this is 3. Here's 1, here's 2, and here's 3. And 4, okay. This is still like in time domain. Right, I have like 1, 2, 3, 4, but I sample it. Now I can redraw it, redraw those, and then my index will be n, so this will be 0, 1, 2, 3, 4, 5, 6, 7, 8. If I redraw it, because this right now is here, but xn, my index is n. Okay, so if I draw the x of n, it should be this is n, and here x of n. So n is 0. We have 1, 2, 3, 4, 5, 6, 7, and 8. 0. So this is n equals 4. This is n equals 8. This is stem plot. We can also write it down, this discrete signal as 0. The value will be 0, 1, 2, 3, 4, 3, 2, 1, and 0. And we have index. If we have like a arrow, that means here n starting from 0. Okay, so here should be 1, 2, 3, 4, 3, 2, 1, 1. Oh, and 0, 0. Now I want to compute the discrete time Fourier transform. Okay, discrete time Fourier transform for this. How can I get the triangle? To get the triangle, I have rectangular pulse, convolve rectangular pulse. I can get a triangle, and the width is 4. Right? So it will be 1, 2, 3, 4, 1, 2, 3, 4, 4 stem part, 4 turns, stands, in convolve another 4 stands. So here, then your discrete time Fourier transform, the multiplication, you should get sine 4/2 omega divided by sine 1/2 omega times exponential minus j times 3/2 omega over square. This times this, they are the same. And why do we have this? Because I shift. Remember that this one, it should be from 0, -2 to 2, and I shift to 0 to 4. When omega equals minus pi over 2, pi over 2, and pi, what is the value of discrete time Fourier transform? That's 0. Next, I have an output. I want to determine the impulse response. Okay, so if I have an output like this, okay, this one, this is like a form here. In this case, what is A and what is D? If I have the difference equation like that, you later on, let me see if we will prove that or not. Well, later on you will see that your impulse response is a to the n unit step function okay, we will do the Fourier transform. If we take the discrete time Fourier transform, we will see this. But first, let's compare that. In this case, D is 3. And how about A? What is A? Here, it's easier, right? D is 3. But how about A? -2. Right? A should be -2. So your impulse response should be -2 to the n un minus u n minus 3. And what is this? We can also write it down. The value, it should be 1 minus 2, 4, 0. And this is from starting from here. And if you plot the impulse response, it looks like one, and then -2, and 4, 0. Okay, so this is n equals 0, n equals 1, n equals 2, and n equals 3. Let's prove this. Okay, if I take the Fourier transform, So let's do the fraction expansion. We do have that. We just separate that two parts. Okay, separate this into two parts. First is 1 divided by 1 plus 2 plus 2 times e to the minus j omega. And then the second one is 1 divided by 1 plus 2 times e to the minus j omega, and then times e to the minus 3 j omega. In this case, when will we have this? I have a phase shift, which means that in time domain, I have a delay. Okay, so I only need to know what this is. Okay, so the inverse will be minus 2 to the n un, and the second term I have minus 8 times minus 2 to the n minus 2 as shift by 3. Okay, and then let's rearrange it. Minus 8 means minus 2 to the third. Here should be minus. And minus 2 to the m minus 3. So overall, you will get minus 2 to the n u n minus 2 to the n u of m minus 3. So when you take the Fourier transform, you will also get the final this result. Now we can determine y, the output. Since we have the impulse response h and also our input signal x, when they do the convolution, we will get the output y. So what is the output y? So the y is x convolved h. And what is x? This, well, either way, if you want to do it in frequency domain and then do the inverse Fourier transform, or here, because here you see that for x we know it is 0, 1, 2, 3, 4, 3, 2, 1, 0, and starting from here 0, and also h is 1, minus 2, 4, 0, starting from 1. When I do the convolution, what is the length of the output y? First, what is the length for x? 9. Okay, so here length is 9. And how long is the impulse response? So overall, when I do the convolution, okay, so now let's have x. Well, which one would you like to flip? x or h. This is shorter, right? It's easier to flip this. So now we have 0. The x is 0, 1, 2, 3, 4, 3, 2, 1, 0. And your h, if I flip, there'll be 0, 4, minus 2, 1, right? So I flip. So what do they do? What do we do? Sliding to the right. Okay, sliding to the right. So first I will have value here, even though it is 0. First one, second one, third one, and so on till the last. Well, you have your nobility or whatever. This is what is that? Good notes. So you can just slide that by yourself. Okay. So overall, your y should be, first is 0, second 1, third 2 minus 2 plus 0, 0. Okay, so you have a 0, 1, 0, 3, 6, 7, 12, 9, 6, 4, 0, 0, and starting here. This method will be easier. You can also do, well, so it really depends if you want to do the multiplication or convolution. If you do the multiplication, good, you have this times this. Okay, this 2. Then you simplify. Okay, you can check the table to simplify it. Or you do the convolution. Remember that this signal, even though I have a 0, this is still my signal. Okay, I should include it. Well, the last one is that what we have done last week for the perfect reconstruction.